Ladies and gentlemen, good morning. Welcome to the webinar on Prognostic methodologies to optimize the remaining useful life of components, products, or systems. Organized by Center for Advances in Reliability and Safety, in short, CAiRS. I'm Jeffrey Chen, Program Manager of CAiRS. I'm delighted to be the MC of this webinar. The webinar today has a professional program to be delivered by local and overseas professional experts and renowned industrialists. We look forward to their sharing of their industrial and research experience on prognostic methodologies to optimize the remaining useful life of components, products, or systems. We are very honored to have Dr. Cao Nu just sit next to me, Associate Professor, the Hong Kong Polytechnic University, to be our guest speaker today. So I think now we can move on to the next presentation. The next presentation is from Dr. Kelvin Poon, Chief Technical Officer, Compass Technology Company Limited. Since Dr. Kevin Poon is not here with us today, but we very appreciate for his presentation of the video presentation. So his topic is Advanced Flexible Substrate Technology Development for Medical Devices and its Reliability Consideration. So now we can play back the video.
Thank you for listening to today's conference. My presentation topic is Advanced Flexible Substrate Technology Development for Medical Device and its Reliability Considerations. So following are the outline of my presentations. When we talk about the new class of home wearables, with the recent pandemic situations, people start to care about their health, their fitness, more than ever before. At the same time, most of the people start to stay at home, even for medical consultations. So there is a need for us to develop a new class of wearable devices for daily use, especially with the advancement of digital transformations. So there are 4 areas always come to our consideration here. First, the device could need to be purposeful, using the latest sensing technology to monitor health parameters such as ECG, EEG, and glucose monitoring. Secondly, the device could need to be smaller in size and lighter in weight. At the same time, it has to be achieve medical-grade accuracy under dynamic conditions, which is typically induced by body movement. Finally, it has to be safe and robust for long-term and daily use. Figure here showing you possible sensor per system combinations to empower and create new class of wearable product. If we talk about the challenge of smart wearable device on flexible electronic, there are a couple of areas we need to stay focused. First is on the biocompatibility for direct skin contact and implant devices. So whether the device is able to withstand to corrosions or chemicals, or the electrode material can be more sustainable and become washable and durable. This can be achieved by using the direct metallization on chemical stable thin film materials or using the noble metals as a surface finishing. Secondly is whether the flexible circuit is capable of cell power, providing a stable power source, and there shouldn't be a chance the battery will be exploded. That is requiring a solid-state thin film battery directly integrated onto the flash circuit. For form factor miniaturizations, the device needs to be provide economic benefit to the user without limiting the number of IC or sensors. This can be achieved by scaling down the circuit dimensions and using a more flexible dielectric materials. Finally, higher functionality can be also achieved by low-volt high-density interconnect technologies, and that's usually requiring a system on fast packaging. For system on fast packaging perspective, there are many different sort of devices to be assembled onto a single package, targeting a small form factors. For example, many active devices, beams, sensors, RF performance-related devices, or shielding layer as well. The capacity of the IC can be fanned out and redistributed using the finite technology of the flexible circuit. So there are many different packaging arts to make it possible for significant form factor reductions For example, we can pack multiple IC and components on both sides of the high-density flash circuit using high-precision assembly bonding technique and having them good top, underfill, or molding and gap situations. The package-on-package can be achieved by multiple refold or epoxy bond using the low-temperature interconnect technique. We can also consider to tie each fast sub-assembly with a tight tolerance to achieve a module-level integrations to further enhance functionalities. As we can see from this diagram, the fast is able to fold and significantly increase the volumetric areas to embed functional materials. For example, battery for energy storage. The selection of the material for fast circuit is also an essential factor that will affect the packaging performance. For example, waveguide material can be embedded within the flexible gas circuit after tuning the reflective index of the dielectric to allow the optical signal transmissions. So in the following sessions, we would like to introduce some of the latest flexible circuit materials to tackle some of the packaging challenge in home use medical devices. Here I would like to introduce a new type of direct metallization materials that is able to produce finite circuitry. This material utilizes a unique surface modification technique. As shown in the videos, the system here is already commercialized in production of flexible circuit at 250 mm format. First, in the modification process, the hydroxyl ions is used to open up the symmetric imide ring, forming a layer of polyamide acid. This PA layers constitute carboxyl and amide bonding is formed after the modification process, which can accelerate the PD absorption rate as well as act as a catalyst to facilitate metallic bonding. Finally, an extremely thin and homogeneous electronic liquid at 100 nanometers can be deposited as a seed layers. This technique is able to produce material that is not only suitable for finite circuitry, but also enable noble metal depositions for biosensor applications. So from the TM analysis and 1 million magnifications, we can see this PA layer is below 5 nanometers, while the deposit nickel layers is only at 100 nanometers. The material produced by this technique is able to withstand the heat treatment even at a temperature of 300 degrees Celsius, despite it being hydrophilic. This is because of the ultra-thin PA layers that allow the rapid moisture uptake, preventing the molecular bond degradations. As a result, a robust bond can be achieved by using this technique to produce the finite circuitry. As we can see from the diagram, the circuit formed by this technique poses an excellent bending endurance and also smooth surface with an hour value below 50 nanometers. The bending cycle is also superior as compared to the conventional sputtering type materials, while the smooth surface also benefits for the significant reduction in conductor loss, and therefore it is ideal for signal transmissions. As shown from the pictures, the materials produced by this technique is suitable for fully additive process with a better trace profile. As we can see from the conventional semi-additive process, the undercut is always posing concern and causing frequent trace adhesion problems when the pitch is go down below 20 micrometers. The fabricated circuitry is proven to pass all the reliability testing, including the adhesion test, bending endurance test, and also with a very stable insulation resistance for finite circuit applications. It is also possible to apply the direct metallization to the other optically transparent thin films such as COP and CAiRS. We would like to introduce a couple of pre-treatment processes prior to the surface modifications. For example, the COP film can be directly metallized by applying the UV treatment. In these cases, the lower UV wavelength is able to produce a higher energy level, which can break the chemical bond of the COP film. As we see from the experimental diagram, the wavelength has to be precise, which is able to convert the environmental oxygen to ocean gas. Plus the another UV treatment, it is able to generate active oxygen to remove the organic compound, forming a covalent bond with carboxyl group for direct metallizations. For metallizing the gas, a newly synthesis layer containing silicon oligomer has been developed, which is able to directly coat on the glass surface to facilitate direct metallizations and full gas-free applications as shown in the middle pictures. Both of these materials offer excellent biocompatibility, low loss, smooth surface, as well as optical transparency. We do see a lot of potential opportunities with direct metallization on these materials, especially for contact lens sensors. As we can see from the pictures, a chipless, battery-free impound sensor is fabricated by using these low-flow materials for glaucoma treatment. Another aspect of miniaturization of flexible electronics is to utilize the thin gauge materials along with the careful selections of material constructions. As we can see from this picture, the thin film dielectric can be 5 micron thick, which allow the flash to fall in a small radius in order to provide better geometric conformance. Another example to showcase how the high-density flash circuit is being assembled in a small form package after sub-assembly with many different IC, sensors, and passive using the copper pillar refold technologies. The flash is then folded in the S shape for a significant volumetric reductions in order to reduce the package size of 3 by 4 mm. These are all possible due to careful selections of the materials with the consideration of the mechanical properties such as its modulus, spring back force, as well as the restoring angle. As you can see, each interface layer is able to withstand both tensile and compressive stress induced by the bending process, which is also robust after 1000 cycles of temp cycling. Another aspect of biocompatibility is for sensing the electrodes with direct skin contact applications, surface finish is moving towards noble metals such as platinum, titanium, and rhodiums. As we can see in the left-hand side image, using the direct metallization technique over the PI film, a homogeneously distributed metal grain structure can be achieved, which is ideally suitable for subsequent noble metal plating to produce excellent plating uniformities with fully protecting the sidewall of electrodes. One major application is dry electrode for ECG detection in glucose monitoring. As we can see from the picture, the platinum is placed over the gold as dry electrode using the direct metallization technique. This can enhance the sensitivity of electrode oxidations of glucose, as well as replace the conventional copper electrodes, which is toxic. Compared to the wet electrode, dry electrode is a promising solution for home use wearables for a couple of reasons. It requires less maintenance because there is no hydrogel involved. Typically, the hydrogel has a shorter lifetime and requires regular replacement by medical professionals. Advancement in system-on-flash packaging must come together with the advancement in high-density interconnect. For packaging of home wearables, it is always demand for high-density interconnect between the IC to substrate and substrate to board level interconnect. As you can see, the bond pitch scaling down requires different type of interconnect technology, from copper pillar refold soldering to diffusion bonding. Current first-level interconnect is already able to achieve the bond pitch below 60 micron using the high-precision thermal compression bonding, adhesive bonding, as well as the ACF, ACP for handling heat-sensitive IC materials. So one example for sensing the electrode, a bond peer array using the vertical gold wire can be high-density bond on the flexible circuit. After the vertical wire is formed, we can apply the biocompatible mold compound to expose only the tips of the gold wire as sensing electrode. One major application is neurosensor to detect the EEG signal for direct skin contact. We could also like to introduce a thin film battery that can be integrated onto the flash circuit for cell power capabilities. Nowadays, all the PCB or flexible circuit alone are powerless, and they are all connected with a rigid and thick battery, which is unable to bend and require additional assembly process such as hot bar soldering or ACF assembly. With the trend of miniaturization, conventional battery cannot be simply placed on the flexible circuit considering small form factor anymore. Conventional battery with liquid state electrolyte is also posing a safety concern, which is critical for home use devices. Therefore, a unique material has been formulated that is directly printable onto the flexible circuit. As we can see in the middle here, there are 4 elements of the material that dictate the performance of the battery. First, the polymer used has to be elastic properties with atmosphere's microstructure that actually improve the flexibility, that is easy to conform and compatible with the flexible circuit materials such as polyimide. Secondly, the lithium-ion salt need to be carrying high ionic conductivities. Also, the ceramic filler is dispersed to improve the bendability of the integrated battery. Finally, the polymer surface is tuned to be sticky enough to ensure proper contact with the interface. This structure is able to improve the ionic mobility and stability during charging and discharging process. It also enables lower contact resistance. Here I could like to show you a high-level process flow of integrated battery fabrications, which is consist of the flexible circuit, battery material preparations, multiple parts of the printing the electrodes, as well as the cell assembly process. The viscosity of the electrodes materials are formulated to be screen printable, making it cost-effective. As shown in the diagram, we can see the integrated battery is below 150 micrometers, which is still flexible enough and can be rechargeable. As we can see from the videos, We cut the solid-state battery is still power on and does not cause any leakage or short circuit, demonstrating. Once the battery is fully integrated onto the system on fast package, we can see a fully functional and rechargeable modules with a couple of advantages. First, all the functionality can be integrated into a single foldable package, which is thin and lightweight. As the IC is directly powered by battery without the external connections, the contact resistance can also be reduced as well. Also, the battery terminal can be integrated into the fast circuit, significantly improve the design flexibility. Here is the brief comparison of the integrated battery performance as compared to the currently available technologies. Basically, the battery offers a significant benefit in terms of the flexibility, maximum discharge current, total fitness and weight, as well as the elimination of external connections. Of course, to achieve this performance, we have the multiple optimization including the electrolyte microstructure as well as the cooling conditions. As you can see from this experimental, a proper separator is important and will affect the C rate and maximum discharge current of the battery. The battery can be also operate at a wide range of temperature from -20 to 60 degrees Celsius due to its atmosphere's polymer matrix with a stable ionic transportations. To improve the reliability performance of the flexible electronics, there are a couple of areas we always need to stay focused. First is the technical characteristic, as the packaging configurations is getting more and more complex, and the IC is stacked with the heterogeneous integrations. And we should expect to see a new class of failure mode induced by any fine pitch interconnect or any interface caused by thermal mismatch, causing long-term reliability issues. So to understand the physics of failure between each process and mechanism behind of each failure mode is become very important in order to predict and improve the product reliability performance. As we can see, the medical devices are targeting for long-term use, which usually has a lifetime of 10 to 15 years. One example is the ECG device used in the smart jacket need to put in the washing machine for over 1,000 cycles. As we can see from this diagram, it suggests that lifetime requirement can be integrated into the DFMEA process in order to precisely sort out all the critical failure mode during the design stage. After that, process characterization can be performed with data collections using the defined measurement tools to generate a robust design. Finally, detailed design can be validated by the process capability study with enough sample size based on the final product yield requirement. This approach is suggested to minimizing the reliability risks while shortening the development cycle time. For long-term reliability perspective, the interconnect always play an important role to improve the performance of the system on fast packaging. For the first stable interconnect, we can see the thermal compression bonding and copper pillar solder joint are the promising assembly technique to achieve the fine pitch bonding. With the reduction of solder volume in copper pillar micropump, the selection of the surface finish and the IMC fitness control always dictate the reliability of the solder joint in long-term run. For the thermal compression bonding, the direct metal-to-metal diffusion is created by the high temperature and pressure sintering processing. The void detection and the bonding interface could be propagated and causing weakened bond in the reliability stress testing. We could also like to show you the future roadmap of advanced flexible circuit. For further miniaturizations, the fast circuit is always demand for more fine-line technologies as well as the tight tolerance on the multi-layer circuitry. Thinner dielectric down to 5 micron PI core is also required to sustain the wheel-to-wheel handling. For plating technology, nickel-free and noble metal plating are on the way to go for biosensor applications. To further improve the performance, more dielectric materials such as fluoropolymer for high speed and high frequency, as well as flexible glass and ceramic for more unique applications. As more and more die have to be interconnected with the flexible circuit, advanced interconnect materials such as nanocomposite are also on the roadmap. Besides silicon and battery, more functionality can also be integrated, such as antenna and waveguide. As we sum up, we have introduced some of the latest flexible circuit technologies, as well as the high-density interconnect for packaging of wearable devices. All of these tackle the challenge of biocompatibilities, cell power, form factor miniaturization, as well as high functionality, which are essential areas for home-use medical devices. So we also suggest to integrate the long-term reliability requirement into the design FMEA in order to improve the robustness of the medical device. Thank you everyone for listening. Hope you enjoy the conference.
Thank you Thank you, Dr. Kevin Poon, for sharing us the experience. And dear audience, please, again, reminded to scan the QR code if you would like to raise questions to our guest speaker. Okay, it's time for the next speaker. Now, let us invite Dr. Kah-Hong Nu, Associate Professor, the Hong Kong Polytechnic University, for presenting. The topic is a sensor-based method for extending the remaining useful lifetime of RGB LED lighting system. Over to you, Dr. Lu.
Thank you, Jeffrey. Okay, let's begin. So let me introduce myself again quickly. I'm Dr. Lu from the Department of Electronic and Information Engineering. So it's a pleasure to be here today. So actually, I would like to thank Professor Yung and also Jeffrey for having me here today. So it's a pleasure as well to meet all of you online. So the topic of my seminar today, well, I should call it webinar today, it's a sensor-based method for extending the remaining useful lifetime of RGB LED lighting system. Right, the title a bit long. But in fact, towards the end of the second part, I would say, of this webinar, I will also introduce another application. So besides RGB LED lighting system, I would also like to introduce another applications that we can apply a prognostic method to extend its useful service lifetime. So let's begin. So since the theme of today's webinar is about prognostic methodology, so I think it's right to hear that we give a quick or brief definition of the word prognostics. So I'm sure most of you have attended Dr. Azarian's webinar this morning, and you all have a good understanding about what prognostics is about. But in case some of you have missed the webinar, I think I will summarize the word prognostic in one sentence, and that is the prediction of the future state of health based on current and historical health condition of, well, it can be any kind of system, but here today we focus on electronic system, which is my main research area. Well, specifically power electronic system. So typically the reason for doing that is that we may be able to use the information obtained from this methodology to predict the remaining useful lifetime of some electronic products. The advantages do so because doing so will allow us to have some advanced warning of failure, so we'll know the system is coming to an end of its service lifetime and will shut it down before it fails catastrophically. So also we may save costs by scheduling the maintenance in a more accurate way. So that's what we call the maintenance forecasting. So by continuously monitoring some parameters or some parts of the system, we also will able to detect some fault in time before it actually causes the system to fail catastrophically. Also, from the information collected, we can actually use the information to improve the design of a system to make it more reliable in the future. So basically, there are three prognostic approaches currently used. And due to time constraint, I will not go through details. So I'm just going to summarize them by just saying the main points here. So the first method involved the use of fuses, canary devices. So basically, the fuses of canary devices, they're designed to fail faster under the same condition as everything else. So basically, it provides an early warning signal to the failure of the system. And the second method is we actually choose some measurable parameters from a system, and we insert some sensors and measure the parameters. As the parameters changes due to aging, so we can actually use the information to predict the remaining useful life of the system or the device. And the third method, instead of monitoring some parameter associated with the device itself, we can also use sensors to measure the environment in which the system operates, and then correlate this to the failure of the system through the use of the physics of failure modeling. So today here, I will focus on the use of the second method. So basically, we will actually measure some parameters online on an RGB lighting system, as well as in the second example, it will be a DC-DC converter and use the information to help us to extend the remaining useful life of the system. As the work was done quite a few years ago, so at that time we were focusing on how to extend the remaining useful life of the systems. And now as I reflect back, maybe we can also further extend the work by including the prediction of the remaining useful life as well. So this could be some of the future research topics that we can pursue here at CAiRS. So I would like to talk about the first example, which is our RGB LED lighting system. So to make a case here, I'd like to contrast an RGB LED lighting system to a white LED lighting system, which is a much cheaper solution. But if you're familiar with white LED system, then we know that actually the color temperature of a white LED will change significantly during its lifetime due to phosphor deterioration, due to lens yellowing, or the changes in some operating condition, for example, the driving current and also the heat dissipation caused by the increased parasitic resistance due to aging. So this kind of color temperature change, they're not compensatable. But so basically, they're permanent and cannot be compensated electronically. So in contrast to that, so RGB LED lighting system provides us with the flexibility of adjusting the color temperature. So as the color temperature of the lighting system changes due to aging, we can basically compensate for those changes and adjust the intensity of each of the three primary colors to restore the original color point. So basically, RGB LED lighting system is more appropriate for applications that demand high color accuracy, such as high-end LCD display or LED projector. Here I'd like to show one example of RGB LED projector based on the use of three primary color LED. So in front of you can see a LED projector based on a DLP technology, where DLP stands for digital lighting processing. So this is one of the very commonly used technology for LED projector. So you can see that actually the white light is obtained from the three primary colors. So we have a micro display there, which is basically an array of mirror, okay, that choose to reflect just the right amount of red, blue, and green light to the screen to create different images. So to maintain a high image quality, of course, we understand that the three primary color LED, they need to provide a stable luminous flux. So therefore, as they age, we need to have a mechanism to ensure that the luminous flux emitted by these three primary color LEDs, they remain constant. So to do that, we use a feedback system to do that, which is a common approach. So basically, we will sample the light emitted by the RGB LED through using photosensors and then compare them with some reference values. And by using a PI controller, the LED driver will always output the right amount of current to make sure that the output of the RGB LED, they follow the reference value. So there are different approaches to do the feedback scheme. So one is a direct flux feedback, and the second one is similar, but the photosensors are installed with filters that try to imitate the color matching function of a human eye. So basically, the information that is fed back by the photosensor will correspond directly to the human perception, color perception. And apart from sampling or measuring the luminous flux, there are actually other methods to do the closed loop, the feedback control of luminous flux. One is by using the forward voltage feedback. Forward voltage can be associated with the junction temperature of the LED. So therefore, when the junction temperature of the LED changes, for example, due to the environment temperature change or due to some other factor, so basically the junction temperature information will be reflected by the forward voltage. And so therefore, we can actually, based on the sense forward voltage, we can calculate the right amount of duty cycle to apply for each color so that to restore the color back to the desired point despite the temperature change. So the second method is by feeding back the electric power of a LED. The idea is very simple. So it also measures the fault voltage of a LED as an indication of the temperature, right? And then to adjust the power delivered to the LED to make sure that all the 3 LEDs will output a stable luminous flux. Now, the drawback of these 2 methods is, as you can say, they depends on the use of lookup table. Okay, lookup table means we need to have some pre-calibrations. And as you can see from the next page here, actually the fault voltage of the LED actually changes as it ages. Okay, so therefore, if we apply the previous 2 methods for color control, then it will require a lot of frequent calibration to maintain the performance of the system. So therefore, the previous 2 methods based on electric power feedback and also fault voltage feedback, they are not suitable to take care of a situation where the the LED system or the luminous flux decays due to aging. So therefore, we think that the photosensors based method would still be the ideal choice for this kind of application. Because there's no calibration needed. Okay, right. So before we go into the control methods, I would like to quickly talk about how we can drive the LED. So here there are 2 examples. So clearly we can use 3 converters to drive 3 primary color LEDs. And another option is that we can use 1 power supply to drive the 3 LEDs sequentially, which means that each LED will be driven 1/3 of the time. So it depends on the different consideration, cost, or utilization of LED. So we can have different options in terms of how to drive the LED. So let's come back to the control. Right, so the control basically can be represented on the block diagram on the right-hand side. So basically, each primary color LED will emit some luminous flux, which is measured by the photo sensor, and the measured value will be compared to a reference value, and the error signal will be used to drive the LED driver, so as to output the correct amount of current to maintain the luminous flux of the LED. So the same is repeated for each primary color LED. But there's a problem in this approach is that we understand that the luminous flux of RGB LED typically decays with aging, so they become dimmer and dimmer. So in order to make sure that they maintain the original intensity, so more power will need to be delivered to the LED. So if we control the current or the power delivered to the LED by using pulse width modulation, that means the duty cycle of the pulse width will have to be increased to compensate for the decaying luminous flux of the LED. But there's a limit to do so because we cannot increase the duty cycle indefinitely. Okay, so up to a certain point, the duty cycle will saturate, right? That is the maximum the conduction time it can have. And another consideration is that if the duty cycle is allowed to increase beyond certain level, the LED may suffer from overheating, and that may accelerate the further degradation. So therefore, we typically will set a maximum duty cycle to which the LED can be driven. So when this maximum duty cycle is reached, basically the system becomes open loop, and therefore there's no way we can continue to regulate the color of the LED. So therefore, we need to have, in order to maintain the color performance of the LED system, then we need to have a different approach here. So before I talk about the proposed control method, I would just like to point out that here, the duty cycle of the PWM signal used to control the luminous intensity of LED can be regarded as a precursor, which it's actually will provide information about the current state of health of the LED, and also it can provide us with information on the remaining useful life of LED. So if we have the data to support this, then what we can say is that, for example, when the duty cycle has reached its maximum value, so if we have data to tell us that when the LED does so, then the remaining lifetime of a LED will be a certain percentage of its normal lifetime. So this is the way that we can make use of the information provided by the PWM duty cycle. Okay, so coming back to the proposed color feedback, to the proposed color feedback control. Here, we understand that after a certain point, the duty cycle of the LED will exceed the maximum value, and the system will lose controllability. So to maintain the controllability of the lighting system, then what we can do is we need to reduce the duty cycle of the PWM signal, and to do that, one way to do that is we reduce the reference value. So that means if we take a look at the red block here, so that corresponds to the red channel of the RGB lighting system. So we actually adjust the capital X value. So if we reduce the reference value, then the duty cycle will be reduced below the maximum value, and therefore the controllability of the system will be restored. But if we only do this change to the red channel and keep the green and the blue channel, the reference value the same, then we will lose control of the color point of the LED system. So therefore, in order to maintain the color point of the total light output, we also need to reduce the reference value for the green channel and the reference value for the blue channel as well. But doing so inevitably will cause the overall luminous flux of the total light output to decrease. But the advantage is that we gain control back of the color performance of the system, and we maintain the color point of the system. So here I'd like to use two examples to illustrate the effectiveness of this the proposed approach. So we have done some aging on the three LEDs, different colors, and we noticed that the three primary color LEDs, they show very different aging behavior. Although they all show a decay of the luminous flux with aging, we can see that some of them actually shows a highly nonlinear behavior during the aging. And also different types of LEDs show different aging behavior. So that means it is very difficult to use a lookup table approach, as was used by the two methods that I mentioned previously to do the color control. So that again highlights the suitability or the appropriateness of using the photosensors to do the feedback, closed-loop feedback, color feedback control. So we actually make use of two different RGB LED made by two manufacturers. So, and then we age them, in an accelerated way, of course. So that's why you notice that the aging time here is very short, but in fact, we have applied very high stress to those LED samples to cause them to deteriorate much quicker. So we can see that on your top right corner, okay, so that shows the duty cycle of applied to the RGB LED as the LEDs age. So we can see that if we look at the blue light, we can see that the blue LED actually the duty cycle increases to its maximum value after around 12 minutes, right? So, and then the duty cycle will maintain there. That means we have lost control of the luminous flux of the blue LED already. But if we look at the green and the red one, that we still have control. So the duty cycle keeps on increasing to compensate for the aging. But in this case, we can see that the color point has definitely changed because we no longer be able to control the luminous flux of the blue LED. So that is the problem with the conventional control methods. So in terms of a color deviation, we can see the figure at the bottom left corner. So we can see that the black curve, okay, corresponds to the case of the conventional control, where we can see that after around 12 minutes, basically the color deviation is so serious that we can consider that the RGB lighting system has reached its end of life at 12 minutes, okay, because of the serious color deviation. But if we use the method that we've proposed, so basically we keep the duty cycle of a blue LED unchanged, but we actually adjust the reference value for the green LED and the red LED so that they will decrease with further aging, so that the ratio between the three colors remains the same. So therefore, we also can maintain the color accuracy after 12 minutes. So we can see that actually the color accuracy can be maintained up to around around 22 minutes, up to 22 minutes, where the luminous flux of the total light output of the LED have dropped to below 70%. So this is another criteria for declaring the end of life of LED system, where the luminous flux has decayed to below 70%. We actually will say that the LED lighting system has reached the end of its life. So therefore, if we use this criteria, apply this criteria to the system that uses the proposed control method, then we can see that the lifetime of the RGB LED has been extended by around 100%. So basically, it's extended from 12 minutes to 23 minutes. So we see another example here, which is another LED module made by another manufacturer. A similar situation happened here, so I will not repeat the details here, but what we can see here is that if we apply the conventional color control methods, the LED module will reach the end of its life at around 245 minutes of aging. But if we apply the proposed control method and use the 70% luminous flux threshold as the criteria for end of life, then the lifetime of the RGB LED module under the proposed control method has been extended to 550 minutes. Again, it's about 2 times the value of compared to conventional methods. So now this method can be extended to a multi-monitor and multi-projector display, where the image is actually made up by combining the images shown, okay, by multiple monitors or multiple projectors. And the requirement is that we expect a uniform display where the boundary, okay, between the monitors, or the boundary between the projector should be smooth, so the entire image should be seamless, should be as uniform as possible. But if each of this monitor, of each of these projectors, they actually have a different state of aging, then what we will see is a situation shown at the bottom right corner, where each projector will output an image which looks very different from the adjacent one. And when all these images are combined together, then it will cause some discomfort to the viewing of the user. So to mitigate this problem, okay, the method that we have proposed can be applied here is that if we allow the projectors to communicate with each other, and they will always share their tri-stimulus reference value with each other, and always select the minimum set of reference values and use it commonly for all the projectors, then we can actually ensure that all the projector will show the same color point, which have the same color performance, despite that each of them may have a different aging state. So this is another possible future application of the proposed methods. Okay, and I would also like to talk about a second example here, if time permits. Okay, so this is another example where we have used the precursor methods to extend the remaining useful life. In this case, we are focusing on the DC-DC converter. So I think most of you know that DC-DC converters are used in many applications. So if we just look at the, for example, our laptop or computers, then DC-DC converters are used to power our CPU, power our hard disk, power our RAM, power our display. So basically, DC-DC converters are everywhere. So to ensure that the DC-DC converter delivered the best and optimum power quality to the load, output voltage regulation and the transient recovery time is important parameters. Both of them are important parameters in high performance DC-DC converter. But just like all other electronic products, DC-DC converters, the components on the DC-DC converters, they also suffer from degradation due to aging. And we find that the performance of DC-DC converter can be adversely affected if this situation is not compensated or is not mitigated. Whereas by using appropriate methods, we can compensate for the aging of the components, and then we can actually extend the useful life of DC converter, as we will show in this example here. So in front of you, you'll see typical configurations of a closed-loop controlled buck converter, which is a step-down DC-DC converter. So on the left-hand side, you can see that the changes in the inductance value and the capacitance value. So here we have included three cases: the nominal value, 25% decrease, and 25% increase in the values of the inductors and capacitor. They will actually cause a significant change, okay, to the frequency response of the converter, and therefore it will affect the closed-loop performance of the converters. So in the extreme case where the capacitance value has decreased by 25%, here we can see that this is an experimental result that we have actually measured on our buck converter examples. So the top figure here shows when both the inductor and capacitance value, they have the nominal value. So everything seems fine. So when we step increase or step decrease the load current, we can see that the output voltage maintains a good regulation. But whereas if we reduce the inductance value from 1.2 to 0.8 microhenry, we can see that the converter becomes unstable. Okay, the same happens when the capacitance value is reduced significantly from 1.1 to 0.81 millifarad. We can also see that the converter has become unstable, right? So as the this is a situation that we can commonly see in a real DC-DC converters, because mainly the output, the capacitors of a DC-DC converter would be electrolytic capacitors. So as they age, they will slowly lose the capacitance. So when they lose the capacitance up to a certain point, then as the experimental results here show, that this situation can potentially destabilize a buck converter. So we can see the dependence of the converters performance on the values of inductance and capacitor by looking at the transfer function of the power stage. So here we see that the power stage has two very important frequencies here: the omega naught, which is the resonant frequency, and the omega ESR, which is the ESR zero frequency of the converter. And you can see that both of these frequency, they depend on the values of the inductance as well as the capacitance. So when the inductance value and the capacitance value change due to aging, so we can see that the power stage of the buck converter will also change significantly in terms of its frequency response. So if we look at how we typically compensate a buck converter, we can see that the frequency, or the zero frequency and the pole frequency that we choose to compensate the power stage we can see that mainly these frequencies, they are related again to the inductance and capacitance value. So therefore, if the power stage of the DC-DC converter changes and we maintain the same controller transfer function, then there will be a mismatch between the two, and that will affect the performance of the DC-DC converter. So what we propose to do is that we can actually, by using the quasi-impulse response of the buck converter, so basically what we do is we apply a short input pulse during the startup of the converter, and then we measure the response of the the filter stage of the buck converter. We will be able to estimate the value of the inductance, capacitance, and therefore, and as well as the resonant frequency. So once we have determined the resonant frequency, then we can adjust the controller parameters accordingly so as to maintain the optimum transient performance of the buck converter. So here's what we did. So we apply a short pulse to the filter of the buck converter, and then we measure the output voltage. So the two cases are possible, but most likely the underdamped response, it's more common considering that the parasitic resistance of the filter will be very small. So we typically encounter underdamped response here. So basically by measuring the difference or the ratio between the two peaks, right, the first peak and the second peak, we will be able to estimate the resonant frequency. And here, the resonant frequency can be used as a precursor to tell us what is the current aging state of the converter, and then how much remaining useful life it's available to us, and whether it's time to do some maintenance. So I would like to highlight one point here is that this action of applying a short pulse, it's during the startup of the converter. So basically this method does not disturb the normal operations of the buck converter. So once it's started up. So this is one part. So I mentioned that there are two critical frequencies here. So we've already measured one frequency using the impulse response. And the second frequency, the ESR0 frequency, which is related to the parasitic resistance of the capacitance, though it can be measured by the steady state output voltage ripple. So I won't go through the maths here, but what we can see here is that if we are able to measure the output voltage ripple, we can use the value of the voltage ripple to estimate the ESR0 frequency, which is another precursor that we can use to estimate the current state of health and also the remaining useful life of a buck converter. So after implementing the proposed, we call it auto-tuning controller, because we can, after obtaining the values of the two critical frequencies, we can update the controller, and then and therefore, in front of you here is actually the test we have done on the buck converter implemented with the auto-tuning controller. Here's the first figure on the top left is the impulse response. So we measure that at the converter's output, and then we use this information to estimate the resonant frequency of the buck converter or of the filter, the second order filter. So after that, we updated the controller, so that we can see that in the two figures at the bottom here, so regardless of a large change in the inductance and the capacitance value, we can see that the converter maintains a very good dynamic response, which is almost identical to the dynamic response of a converter when the inductor and the capacitor take their nominal values. So that means we can maintain the performance, the closed-loop performance of a DC-DC converter, of the buck converter, despite serious degradations of the inductors or the capacitance due to aging. So in this sense, we're able to extend the remaining useful life of the buck converter by quite a large margin here, okay, by tuning our controller in response to the change in the component values. So here's the conclusion. So we have presented two case studies here. So the first method is the color control method, which is able to prolong the useful life of RGB lighting system. Okay, so by basically adjusting the tri-stimulus value accordingly in view of the or in response to the changing duty cycle of the PWM signal, which is an indication of the aging state of the LED. And the second example is we've also presented an auto-tuning controller, which is able to achieve a stable and consistently high dynamic performance of a buck converter despite significant change in the inductance and the capacitance values. And as a result, we're able to prolong the useful lifetime of a buck converter. So here, I hope that I have demonstrated how we can use the prognostic methodology to extend the remaining useful lifetime of some electronic systems. So here I've shown the two examples, and I think we can apply the same methodology in many other different electronic products and systems as well. So to end, right, I would like to just do a bit of promotion. Right, so there are actually other projects at CAiRS related to lifetime prediction, related to fault detection. So if you are interested and would like to apply some of this methodology to your products, so you're welcome to collaborate with us. So you're welcome to either contact Professor Young or myself, and our emails are given here. So thank you very much for listening. And it's been, I think, quite a long presentation. So thank you for your patience. I'll pass the time back to Jeffrey. Jeffrey, back to you. Thank you.
Thank you, Dr. Liu, for your remarkable presentation. And I believe that the research is very practical, actually. Thank you for all the speakers for your presentation in this morning. And I hope that all of you find this sharing practical, useful, and inspirational. So in the following time, I would like to proceed the Q&A session for the part 2 presentation for Dr. Liu. So let me see what questions we have. I can see quite a number of questions.
Oh, okay.
Okay, the first one. For DC to DC converter, other than transient recovery time and output voltage regulation, would there be additional important parameters in high-performance DC to DC converters?
Well, I think this is, because we have to ensure, okay, it depends on applications. So we typically want to ensure that the output voltage is well regulated, so that it does not actually trigger some undervoltage lockouts or undervoltage or overvoltage problem, which can damage the load being driven, for example, the CPU, or for example, some computer devices that are connected to it. So in my opinion, for DC-DC converter or for any power electronic system, power quality is always our first priority. So therefore, as a power electronic researcher, so basically this has been a goal that we're trying to achieve right throughout my research career, that we are trying to maintain or trying to achieve the best power quality that we deliver to the load. So either by choosing more appropriate converter topologies, or by choosing a more appropriate feedback control methods. So our target is always to ensure the power quality delivered by the DC-DC converter or any other types of converters. So in my opinion, I think this is the most important design objective of power converters. Yeah.
Thank you. So another question is it possible to use canary approach or physics of failure approach to the remaining useful life prediction in LED or bulk converter application?
I think fuse is always possible because I think all converter, they usually will have a fuse at the input just in case that the current, there's some case of overcurrent, then always the fuse will act to protect the converter from being damaged by the overcurrent. So I think a fuse is definitely possible in the case of converters. So for physics of failure, and this is more difficult because as we can, it's possible, but more difficult because we are talking about a converter, which is a rather complex system. So it is quite difficult to actually model the physics of the whole system. We can, of course, select one or two critical components, and we can develop the physics of failure model of that component by repeated experiments in the lab, by basically stressing it with different stressing factors, for example, temperature, humidity, different power levels. I think it's possible and also quite feasible to do it for one or two components. But if we are talking about the whole converter, then basically the factors that are affecting the failure of the converter is too many. So basically the data-driven approach, in my opinion, okay, a data-driven approach would be a much more suitable solution, I think.
Thank you. So I can see more and more questions are coming actually. The other question is that beside of power cycling stress, any other stress will contribute LED life decay. Is there any theoretical methods or reference equation for supporting LED aging life prediction? Thank you.
Right. I think in this, maybe Professor Jung is more expert on the LED because I'm mainly dealing with the design of the driver, the control. So I have to admit that I do not have very deep research on the body of LED and also its degradation mechanism. I think there's an expert sitting next to me about the physics of failure modeling of LED and so maybe Professor Jung, do you want to comment?
Well, thank you, Dr. Liu. I'm not expert, but we did quite a number of research projects in LED, including high power LED in the past. Now, making LED, you can say it's very simple, but you can say it's very complex processes, including the design and the material science and the processes technologies. Well, it cannot be talked about in this particular morning, but you can go to our website, you can see some of our research reports. But all in all, because of we're talking about physics of failure, and in terms of physics, or failure mode of LED, you can look at the LED itself, including the body structure, the glass, and all the critical components in making LED. Right? Of course, we have phosphor and all these processing sub-material to be added on in the process of making LED. And those are also good contributing to physics of failure consideration as well. So all in all, if you are interested, please go to our website.
Thank you, Professor Jung. Thank you.
Thank you. This question is about DC to DC bulk converter. You described capacitor and inductor values change during the degradation. So the question is that what kind of monitoring parameters are associated with evaluating degradation in the inductors, like junction temperature and internal resistance in case of LED and capacitor, respectively?
Okay, I'll talk about the DC-DC converter. So, while we can measure this indirectly, as I mentioned in the presentation, is that we can use the quasi-impulse response method to measure the resonant frequency or estimate the resonant frequency of the LC filter. So in this case, we don't distinguish between L and C because both of them actually determined together. They determine the resonant frequency of the DC-DC converter. But from the change in the resonance frequency, we can actually correlate that to the change in the capacitance value and the inductance value. So from our experience, that usually inductance will degrade much slower compared to capacitance. So most likely the change in the resonant frequency is due to the change in the capacitance, in particular the electrolytic capacitance. So another way to confirm this is that we also mentioned about measuring the ripple voltage to estimate the ESR0 frequency. So from a change in the ripple size, we can correlate that to the change in the ESR of the electrolytic capacitor. And that will also reflect the aging state of the capacitance. So there are actually two ways that we identify, or we can monitor, or we measure the change in the inductance and capacitance value, although indirectly. So I think the more direct, for capacitance, I think the method that we propose is more direct because we actually measure the voltage ripple, which can be correlated directly to the ESR. So the ESR, I think some researchers have already proven that as the electrolytic capacitor ages, the ESR value will increase with aging time. So therefore, an increase in the ESR is a good evidence of the aging of the capacitance value. And then because the resonant frequency that we obtain from the quasi-impulse response, they involve both the L and C. So if we combine this information with the ESR zero frequency that we have obtained from the another methods, okay, then we can actually have some good guess about the change in the inductance and the capacitance value of the buck converter. But I have to admit that in the test that we presented in the PowerPoint, we have exaggerated the change in the inductance. Usually the inductance will change much slowly or compared to the capacitance value, but we would just want to illustrate the idea that if there is such a huge change in L and C, then they will potentially cause the instability to the DC-DC converter. But in practice, I think the problem of an electrolytic capacitor will be much more serious and deserve more attention compared to the inductance. Yeah.
Thank you.
Yeah.
I think one more question. This question is about the lookup table.
Yeah.
The lookup table requires frequent updates or calibration due to the aging of the lamp.
Yep.
And if we study the aging of the lamp thoroughly and record the necessary parameters of the aging behavior, do you think we can still use the lookup table and the lookup table is still a good approach?
The lookup table, it's always a cost-effective approach, and we should use it whenever it's possible. But as I mentioned here is that we need to frequently update the lookup table, right, as the LED ages or other device ages. So basically, if this is used in a real product, I think this will be quite difficult because it's quite impossible that you do this recalibration at the customer site. Okay, I think this is not acceptable to most customers. So in this case, I think the photosensor method will still be, I think, much more appropriate in this case. Yeah, not to say that every device is different. So that means we cannot just have one calibration for all LEDs because every one of them is different. So for each product, we have to do the calibrations differently. So if you're talking about an equipment that costs a few million, I think this calibration is perfectly fine. But if we're talking about LED lighting system, I think this is just too costly to do if you have to frequently update the lookup table. This is my personal opinion.
Yeah, understand.
Yeah.
Okay, I think the time is up, and thank you for all the guest speakers for sharing your specialized know-how on prognostic methodology to optimize the remaining useful life of components, products, or systems. Okay, ladies and gentlemen, we are very honored to have Professor Vinko Jung, Center Director and Executive Director of CAiRS, to be here with us today to offer a closing remark before we end this webinar. Professor Jung, please.
Thank you, Jeffrey. And I'd like to take this opportunity to thank all our speakers in Section 1 and in Section 2. In Section 1, we have Dr. Asarian from CAiRS of University of Maryland, who talked to us on very unique topics, including the fusion of DDM and POF approach in safety and reliability. And the second topic he spoke on is on the sensors technology, which are very useful. And in the second section, we have industrialist, Dr. Poon of Compass, who talked to us something on medical industry, particularly critical components. They are making critical components for health industry. And last but not least, we thank Dr. Lu in making a very good talk on power devices, and particularly on LED and DC converter. Now, particularly in the second section, we are talking something about very two unique industry in Hong Kong, medical industry and power electronics. I think a few weeks back, some of my industry friends told me that in the future, or actually in the coming few years, power electronics and medical industry will be the two of the most promising industries to be developed and to be supported by the Hong Kong government. So we need a lot of researchers and industrialists to come together to give us some enlightenment how we can move forward to develop these two kinds of technologies and make contribution to these two industries. Now, this particular webinar is organized by CAiRS, CAiRS, Center for Advances in Reliability Safety. We established in Hong Kong Science Park last year, and our research goal is very simple, using big data analytics and DDM methodologies, including ANN, machine learning, plus physics of failure approach and reliability modeling. And hopefully, we can contribute to the industry to make their products and systems very much high reliability and safety levels. So our past events, I think we have conducted, including today, we have conducted 4 webinars and 1 full-day seminars. And for each of these events, we always pull in not only colleagues from academia, but also friends from the industry. We hope whatever we do in terms of research, it can be readily available and applicable to different industries. So all in all, if our audience, you have anything that you think CAiRS can help, please contact us, and you can have a lot of more information in our website. Currently, we have more than 20 industry companies and organizations, associations, and enterprises who have been in research collaboration with us. So I hope we can contribute to your business, helping you in promoting and elevating safety and reliability of your product and systems and components. So with that, once again, thank you for all the audience spending the whole morning listening to all these speakers And I hope all this knowledge can be useful and applicable in your business. So we look forward for your participation in the next coming event. Thank you.